Here is a graphical explanation of the decomposition of the sums of squares. So we have some data here and one x variable. And you see that a regression line is fit to this data. And the same data is also over here in blue. So you see this point is that point, this point is this point, and so forth. So this is the same data without the x variable. And you have the average here, y bar, and you have in pink one standard deviation above and one standard deviation below the average. And in the regression line, I have also added one standard deviation, or one standard error actually, error bars. I'm saying standard error because it refers to the error over the mean rather than individual observation. So what you see here is that one standard error, the pink bar, or one standard error above, one below, is a lot smaller than the standard error bar over here. That means that by using regression, and we only have one x variable here, the variation inherent in y, so the total sums of squares divided by some constant, is greatly reduced by introducing that x variable. So the model explained most of the variation, and there's some variation still left. So you will also see that the error bar here is constant. So regardless of where I am at which x value, the variation in terms of one standard deviation above, a standard error above and one standard error below is constant. That's by assumption. Regression assumes, a linear regression assumes a constant variance, constant with respect to changing values in x. All right. So there's a second explanation. We can also motivate R squared from the estimates of sigma squared from the intercept-only model relative to the estimate from the full model. So the intercept-only model is the model where I have only here the intercept in here. So y equals beta 0 plus epsilon. And the full model is, well, the usual one. On the previous slide, we just had one x variable. In general, of course, we have many. So this intercept-only model actually also corresponds to the graph on the last slide. I'm going to go back one. See, this is the regression model corresponding, or the graph corresponding to the intercept-only model. The intercept is estimated with y bar, which is this value. We don't have an x value, so we don't vary to the left and right. It's just one level here. And this is the variation over the estimate of beta 0, where beta 0 is the average here. Okay, so there is yet another graphical explanation. And this is completely complementary. If you are happy with the first explanation, that's good enough. This is an additional explanation. In this example here, we have only 4 points, 1, 2, 3, 4. And we have the 4 points in both graphs. One graph corresponds to the intercept-only model, y equals beta 0. So as you change the level of x, the value of y always changes. This is the average value, which is 4 here. And yeah, if you average those 4 values out, you get exactly 4. And then the second model is the regression model, where you have one x variable. Now we are decomposing the sums of squares. squares. And when you have squares, then we know that the square can be represented by an area. So if this is the predicted value here, y equals 4, and this is the value in the data, y equals 5 point something, 5 point, I don't know, 5. Then I have the residual as the difference. And because I'm squaring the residual, the contribution to the sums of squares is this area, this big reddish area. And for a smaller value here, I have a smaller residual and a correspondingly smaller area square. Likewise, for the negative values, the residual goes up here, and then I still have areas. So the total sums of squares is the sum of these 4 areas. And if we now switch over to the other model, the actual regression model, not just the intercept-only model, we see that we can do the same thing. Of course, the predicted values vary. They're not constantly 4. But we still drop down to the prediction line, and then we construct our square. And you see that the sum of the squares here that are still errors are a lot smaller than the sum of the squares over here. And so what the regression does is the regression model accounts for the difference between the sum of squares over here, the sum of the areas, and the sum of squares over here, the much smaller areas. As I said, this is a supplementary explanation. If you were happy with the first graphical explanation, that's perfectly good enough. All right. Now we have a question coming up. I have a regression here on 2 variables. This is actually the return of the IBM stock, and this is the return of the S&P 500. I think those were monthly data. How many observations do we have? We have 30 observations here. And we know this is this ANOVA table, analysis of variance. And the ANOVA table gives us the sums of squares for the model, the sums of squares for the residuals, so sums of squares regression, sums of squares error, and the total sums of squares. So if you add this and that, you get this number here. The question is, what is R squared? So I've blocked this number out, and I've removed the adjusted R squared just for good measure. And that's for you to compute. So this concludes the end of this segment.